Hello students, I am Dr. G.S. Sodhi. Today I bring you the first learning episode in BSc Forensic Science on an important unit of the paper titled Technological Methods in Forensic Science, that is Introduction to Instrumental Methods and Chromatography. General Principles. In this learning episode, we shall learn about module number 1, Introduction to Instrumental Methods, module 2, Overview of Chromatography, module 3, Basic Elements of Chromatography, module 4, Classification of Chromatography, module 5, Principle of Chromatography, module 6, Theory of Chromatography, module 7, Importance of Chromatography in Forensic Science, module 8, Conclusion. The instrumental analysis is an exciting and interesting part of chemical analysis which interacts with every aspect of chemistry and with many other fields of pure and applied sciences. Analysis of Martian soil, the body fluids of race horses and Olympic athletes, the engine oil of commercial and military jet aircrafts, and even the shroud of Turin are examples of problems that require instrumental techniques. The analytical techniques used in instrumentation play an important role in the production and evaluation of new products and in the production of consumers and the environment. Lower the detection limits are achieved by instrumental analysis, which is much needed to assure safe foods, water, air and drugs. The manufacturing of materials whose composition must be known precisely, such as the substances used in integrated circuits, is monitored by analytical instruments. The large sample throughputs made possible by automated instrumentation often relieve the analyst of the tedious tasks associated with chemical analysis. Thus, the analyst is free to examine components of the analytical system such as sampling methods, data treatment and the evaluation of results. Classification of instrumental techniques. Most instrumental techniques fit into one of the three principal areas: spectroscopy, electrochemistry and chromatography. Table 1, Types of chemical instrumentation techniques. Spectroscopic techniques: ultraviolet and visible spectrophotometry, fluorescence and phosphorescence spectrophotometry, atomic spectrometry, both emission and absorption, infrared spectrophotometry, Raman spectroscopy. X-ray spectroscopy, radiochemical techniques including activation analysis, nuclear magnetic resonance spectroscopy, electron spin resonance spectroscopy. Electrochemical techniques: potentiometry, pH and ion selective electrodes, voltammetry, amperometric techniques, coulometry, electrogravimetry, conductance techniques. Chromatographic techniques: gas chromatography, high performance liquid chromatographic techniques, miscellaneous techniques, thermal analysis, kinetic techniques, hyphenated techniques, GCMS, which means gas chromatography, mass spectrometry, ICP-MS, inductively coupled plasma mass spectrometry, GCIR, gas chromatography, infrared spectroscopy, MS-MS, mass spectrometry, mass spectrometry. Although several important techniques including mass spectrometry and thermal analysis do not fit conveniently into these classifications, these three areas do provide a basis for a systematic study of chemical instrumentation. Different types of chemical instrumentation techniques are shown on your screen. The techniques of chromatography are partially non-destructive in nature for resolving multi-component mixtures of minor, major and trace components into its individual fractions. For solids, liquids and gases, different variations are applied. Though chromatographic technique is primarily used as a separation tool, it can also be used for qualitative and quantitative determinations. Nonetheless, final identification generally requires confirmation by some other analytical procedure such as infrared spectroscopy, nuclear magnetic resonance or mass spectrometry. Quantitative analysis can be carried out by measuring the area of the chromatographic peak. Hence, chromatography can be used for qualitative and quantitative analysis. The technique of chromatography was first invented by a botanist M. Sweat in the year 1906 in Warsaw. Sweat in that very year was successful in separating xanthophyll, chlorophyll and various other colored components through a column of calcium carbonate by percolating the extracts of vegetables. So, it used a column which acted as an adsorbent and the various components got adsorbed to different positions on the column. He termed the system of colored bands as chromatogram. Although the term chromatography is based on the Greek words chroma means color and graphos means writing, the term chromatography is a misnomer as majority of the chromatographic procedures do not involve any colored products. Substantial advancement has ever since been made and the method is used to separate colored as well as colorless substances. In 1930s, thin layer chromatography and ion exchange chromatography were introduced as separation techniques. Martin and Singe introduced partition and paper chromatography in 1941 and gas chromatography in 1952. During the next decade, the usual technique of chromatography as a separation process turned out to be universal and has been extended to several areas of study, especially chemistry, biology and medicine. Apart from its use in analysis, it is becoming a potential technique for purifying compounds in pharmaceutical industry and for production of pure chemicals. The recent developments in the field of biosciences are attributed to the chromatographic separation techniques of biomolecules. The technique of chromatography is probably the most important single analytical technique which is used today and is likely to continue to be so in the foreseeable future. Chromatographic techniques is the foundation of molecular analytical chemistry. Recently, its coupling with atomic absorption spectroscopy has extended its application to elemental analysis. The information achieved through the technique of gas chromatography is mainly beneficial to the organic chemist or biochemist who requires to know about the material synthesized by him in the laboratory or separated from living tissue as a part of his research assignment. In addition, it is valuable to the industrial scientist who wants to know the composition of his competitors' products as well as to other scientists involved in characterization of matter. It can also be used as a method for preparing ultra pure compounds such as in the pharmaceutical industry or in the manufacture of pure chemicals. Definition of chromatography. Chromatography is defined as the method of separating the mixture of components into its individual components by an equilibrium distribution between two phases. The chromatographic technique is principally based on the differences in the rate by which the components in a mixture moves or flows through the porous medium, also known as stationary phase, under the influence of some gas or solvent which is also known as the mobile phase. In general, the chromatographic technique consists of the following steps. Number 1, retention or adsorption of substances on the stationary phase. Number 2, separation of the adsorbed substances by the mobile phase. Number 3, elution, the method in which the separated substances are recovered from the continuous flow of mobile phase. Number 4, qualitative and quantitatively analyzing the eluted substances. The technique of chromatography operates under a mobile phase and a stationary phase. The stationary phase is the static phase and the mobile phase is the mobile phase. As the mobile phase continues to travel through the stationary phase, it takes up the compounds with it. The different components of the compound get adsorbed, which are to be separated at different points in stationary phase. This movement of the mobile phase over the stationary phase results in the separation of the different components via chromatography. In case of thin layer chromatography and paper chromatography, the solvent is chosen as the mobile phase. In case of paper chromatography, a piece of paper or strip is chosen as the stationary phase, which is placed in the solvent, whereas in case of thin layer chromatography, stationary phase comprises of a thin layer cell. The technique of thin layer chromatography and paper chromatography operates via the capillary action principle such that the solvent moves through the stationary phase. Chromatographic techniques are classified based on the type of stationary and mobile phases used. Solid or liquid can be chosen as the stationary phase, whereas a liquid or gas serves as the mobile phase. Separation occurs because two or more factors combine, such as capillary action, rates of migration, extent of adsorption, etc. For example, in column adsorption chromatography, a liquid mobile phase is allowed to percolate down as a solid stationary phase, generally packed in a vertical glass column. The stationary phase competes for the solute by adsorption and the liquid mobile phase competes for the solute by dissolution. The method is termed as partition chromatography when both the phases are liquids. These two liquids are immiscible. Generally, partition chromatography is performed by coating the solid support with a liquid to be used as a stationary phase. Sometimes the chemical bonds hold the liquid phase to the solid support. The liquid thus gets immobilized. The partition phenomena in this case are due to the difference in the solubilities of the solutes in the two liquids. In thin layer chromatography, that is TLC, the stationary phase is a thin layer of finely divided adsorbent solid spread over a glass plate. The mobile phase is a liquid. In gas liquid chromatography, that is GLC, the separation is achieved by partition between a mobile gas phase and a stationary liquid phase on solid support packed in a column. Paper chromatography is essentially same as the column chromatography, except that the packed column is replaced by a filter paper strip. The mobile phase is a liquid. If the separation is carried out by allowing the liquid mobile phase to move downwards or descend, then the method is called as descending paper chromatography. And if the mobile phase is allowed to move upwards or ascend, then the method is called ascending paper chromatography. The various types of chromatographic techniques are tabulated in table which is shown on your screen. Table 1, various types of chromatographic techniques. Technique, stationary phase and mobile phase. Liquid solid or adsorption chromatography, as in HPLC, the stationary phase is solid, mobile phase is liquid. Liquid-liquid or partition chromatography, that is LLC, where stationary phase is liquid and mobile phase is also liquid. Paper chromatography, liquid-liquid. Thin layer chromatography, liquid or solid, then liquid. Gas liquid chromatography, GLC, liquid, gas. Gas solid chromatography, GSC, solid, gas. Ion exchange chromatography, solid, liquid. Gel permeation chromatography or size exclusion chromatography, that is GPC, solid matrix, liquid. A more recent development in liquid-liquid chromatography is the countercurrent chromatography, which entirely eliminates the use of a solid matrix support. Further, in gel exclusion chromatography, the stationary phase is a porous gel and the separation takes place in accordance with the size of molecules in the gel. In affinity chromatography, also known as bioaffinity chromatography, separations are done using gels modified to develop higher affinity for specific biochemical reactions. Other modifications of this technique are metal chelate chromatography, ligand exchange chromatography and dye-ligand affinity chromatography. Lastly, the technique that makes use of all the above principles and permits very rapid separation is high performance liquid chromatography called HPLC. The basis of the theoretical discussion in this module will be concerned with partition, adsorption and gas liquid chromatography. With suitable modification, these concepts can be applied to other types as well. The different types of chromatographic techniques are based on the distribution of partition coefficient that is used to describe the way by which a component distributes itself between two immiscible phases. The compound which distributes itself in two equal volumes of two immiscible solvents A and B, the value for this coefficient is a constant at a given temperature and is given by the expression concentration in solvent A divided by concentration in solvent B is equal to Kd. The distribution of a compound, however, is described not only in terms of its allocation between two solvents, but also by its distribution between any two phases such as solid oblique liquid or gas liquid phases. All chromatographic systems consist of two phases. The stationary phase, which can be solid, gel, liquid or a solid with liquid immobilized on it. The second phase, that is the mobile phase, can be liquid or gaseous and flows over or through the stationary phase. The stationary and mobile phases are chosen in a way such that the components are separated based on the different distribution coefficient. This is accomplished by 1. An adsorption equilibrium between a stationary solid and a mobile liquid phase. This is adsorption chromatography. 2. Partition equilibrium between a stationary liquid or semi-liquid and a mobile liquid phase. 3. Partition equilibrium between a stationary liquid and a mobile gaseous phase. 4. Ion exchange equilibrium between an ion exchange resin stationary phase and a mobile electrolyte phase. 5. Equilibrium between a liquid phase inside and outside a porous structure or molecular sieve. 6. An equilibrium between a macromolecule and a small molecule for which it has a high biological specificity and hence affinity. The chromatographic columns are considered to consist of a number of imaginary closed zones, in each of which there is a sufficient space for the solute to attain absolute equilibrium between the mobile and stationary phases. Each zone is denoted as a theoretical plate, and its length in the column between the two zones is called the plate height, which has dimensions of length. More efficient is the column, greater is the number of theoretical plates that are involved, and lesser is the plate height. The separations involved in chromatography can go in for one of the two ways available: column chromatography, wherein the stationary phase is packed into a glass or metal column, and planar chromatography, where stationary phase is present on a planar surface like in thin layer chromatography and paper chromatography. Both these modes of chromatography have their specific advantages, applications, and methods of operation. Two theories have been put forward regarding the rate of migration of solute and the development of peaks in the chromatogram. They are the plate theory and the rate theory, or the kinetic theory. According to the plate theory developed by Martin and Sinch, a chromatographic column consists of a series of imaginary, discrete yet continuous horizontal layers that are termed as theoretical plates. An equilibration of the solute among the stationary and the mobile phases takes place at each of these plates. Migration of the solute is then assumed to occur by a series of stepwise transfers between one plate to the other immediately below. The efficiency of partition in a chromatographic column gets increased as the number of theoretical plates increases. This is because the quantity of equilibration will also correspondingly increase. Next, the rate theory. Rate theory explains the effect of variables, for example, the process of diffusion and mobile phases velocity, so as to decide the width of an elution band. It relates to the effects of these variables on the time taken by a solute to make its appearance at the end of the column. A molecule alternates rapidly between adsorbed and desorbed states. The time which the molecule spends in any one phase depends on the accidental energy gained by the molecule from its environment and is highly variable. A particle can migrate only if it is present in the mobile phase, and as a result the migration down the column is also highly irregular. Consequently, some solute molecules may migrate rapidly while the others may lag behind. The net result of all these random individual processes is a symmetric distribution of velocities around the mean value, which represents the behavior of the most common distribution of velocities or average particle. The width of zone gets increased as it migrates down the column, because more time is needed for migration to take place. Hence, the zone width is directly related to the residence or retention time on the column and inversely proportional to the mobile phase velocity. Let us now learn about the applications of different chromatographic techniques that we have discussed in earlier sections. Paper chromatography has been used for separation of mixtures having polar and non-polar compounds such as amino acids, hormones, drugs, and other biomolecules. Quantitative determination of high molecular weight compounds, particularly in medical and biological research. Thin layer chromatography has been applied virtually in all areas of analysis, including chemistry, biochemistry, biology, industrial, agricultural, environmental, food, pharmaceutical, clinical, natural products, toxicology, forensics, plant science, bacteriology, and entomology. Separation of inorganic ions such as zinc and iron, separation of amino acids and vitamins by the method of thin layer chromatography. HPTLC is also used in analyzing the purity and efficacy of many pharmaceutical preparations and dosage forms. The method can be used for qualitative control and stability testing of different dosage forms such as tablets and capsules, as well as for bulk drug analysis. HPLTC is used in the fingerprinting analysis of drugs of natural origin. The method of HPTLC is used for the purpose of purity control in case of pesticides, chemicals, water analysis and steroids. HPTLC is useful in detecting chemicals of forensic concern, including drugs of abuse, poisons, adulterations, chemical weapons and illicit drugs. Biochemical screening for genetic disorders. There are a number of amino acid markers and acyl carnitines which are measured in dried blood spots after extraction and derivatization in microtiter plates. Screening strategies have been developed for galactosemia, sickle cell anemia and lysosomal disorders. All this is measured by techniques of liquid chromatography and HPLC. HPLC is employed in therapeutic drug monitoring and toxicology. Forensic applications of HPLC include the analysis of drugs, analysis of explosives, ink analysis in case of question documents, dyes in illicit drugs, fibers, lipstick smears, foods and comparison of soil samples, etc. Forensic and criminal cases such as analysis of ethanol in blood, prohibition cases for the percent of ethanol in alcohol, analysis of drugs, mixture of one or more components, chemical identification in individual substances, etc. is carried out by gas chromatography. Gas chromatography, differential mobility spectrometry, that is GC-DMS, is used as a tool for analysis of ignitable liquids from fire debris. In addition to the applications mentioned in this paper, such materials as perfumes, coatings, plastics, oils, solvents and poisons readily lend themselves to chromatographic analysis. The technique of chromatography was first invented by a botanist Sweat in the year 1906 when he separated xanthophyll, chlorophyll and various other colored components through a column of calcium carbonate by percolating the different vegetable extracts. The technique of chromatography is partially non-destructive in nature for resolving multi-component mixtures of minor, major and trace components into its individual fractions. Different variations may be applied to solids, liquids and gases. While chromatography may be applied both quantitatively and qualitatively, it is primarily a separation tool. The principle to chromatographic technique basically operates on the movement of a mobile phase over the stationary phase, resulting in the separation of dissolved components based on their affinities, which can be expressed in terms of its partition coefficient. The stationary and mobile phases are chosen in a way such that the components are separated based on the different distribution coefficient. This is obtained by setting up an adsorption equilibrium between a stationary solid and a mobile liquid phase. This is adsorption chromatography. A partition equilibrium between a stationary liquid or semi-liquid and a mobile liquid phase, a partition equilibrium between a stationary liquid and a mobile gaseous phase, an ion exchange equilibrium between an ion exchange resin stationary phase and a mobile electrolyte phase, an equilibrium between a liquid phase inside and outside a porous structure or molecular sieve, and an equilibrium between a macromolecule and a small molecule for which it has a high biological specificity and hence affinity. The different techniques. Chromatographic techniques have a varied range of applications that aid in several analytical problems and aid in crime scene investigations also. With all this information, here we come to an end of today's lecture. Do keep in mind what we discussed today. I will be back with one more lecture in this series. If you want to learn more and enhance your knowledge, you may log on to our website www.cec.nic.in for MCQ, quizzes, LORs, etc. Thank you for your time today. I will see you in the next lecture. Have a great day.